Let's start.
Ma'am, if it's possible, can you explain the limiting molar conductivity again?
Limiting molar conductivity. Okay. Yeah. What I have done.
Ma'am, electrochemistry is coming till a very certain point in the exam. Did we finish
Ah,
that part in the
no,
last video, or do we
we are
still
doing
have it?
that. Little bit is
Okay.
left. We are doing that
Okay.
only.
So, is it safe to say today's class will be the last one?
For the portion which are coming in exam, but we will finish this chapter today.
Oh,
For
we're
that
finishing
portion we
that
start.
for the.
Hmm.
Is the portion for exam over or not?
No,
No, right?
today we will do. Finish.
Oh, okay.
Nikita, you ask something?
Nothing. I was just asking if you're finishing the portions today.
Ma'am,
Yes.
ma'am, do you have the meeting? I mean, the recording for the last class.
Yeah.
When I recorded it, it got corrupted and it didn't save. So
Okay, I will share it.
yeah, thank you. Like
Okay,
I have half of it, but the
it's
other
fine.
half is not.
I will share both the recordings with you. You
Okay.
just.
Okay. Yeah, the first one I saw already.
Okay, in last class, we have started with conductance. We will discuss briefly what we have done in the last class because many have missed this class. So, Viksha, what is the last topic we have done? Limiting
Like
molar
this.
before Kohlrausch law, right?
No,
Last
I
we-
wasn't there last class.
Right. Who all were there? Adarsh was there, Pavan and Advika. I think all three were there. Adarsh, any one of you can tell me what is the last topic we have done?
Yeah, ma'am. Once again, just checking.
The recording it stopped till the limiting molar conductivity for a weak electrolyte.
Okay, right. Before Kohlrausch law. Thank you. Okay, all of you listen carefully. I will just briefly repeat what we have done in the last class. We have done maximum the physics part. As you all know, what is Ohm's law? V is equal to IR. The current flowing through the conductor is directly proportional to the potential difference applied across the ends. And where R is the resistance is the restriction to the flow of current. So R, we have done this. R is directly proportional to length of the conductor, inversely linked with area. And if you remove the proportionality sign, we add one constant, which is rho. Nikita, you know what is rho here?
I forgot. I know this, but I forgot.
Rho is conductivity. And L by A is called cell constant. And it is denoted by length by area. It is called cell constant denoted by G star. R is equal to rho L by A, which is L by A is called cell constant G star. Its value is constant for a particular cell. And
Is rho conductivity or resistivity?
oh, my mistake, I wrote conductivity. Rho is resistivity. Yeah. And then after that, we have done G, which is a conductance. It is the reciprocal of resistance. And its units are ohm inverse or Simon, denoted by capital S. Then we have there is a one term which is known as kappa, which is conductivity. You can say it K also, but mainly we pronounce it by kappa. Conductivity. Conductivity is the inverse of resistivity. Conductance is the inverse of resistance. Kappa is the inverse of resistivity, 1 by rho. And its unit is, rho unit is ohm meter. So its unit becomes ohm inverse, meter inverse. Or you can say it is Simon meter inverse or centimeter inverse. And there is one small derivation here. Ki rho ko we can also write R A by L. Because R is equal to rho L by A, rho becomes R A by L. So we can say that kappa into R is equal to L by A, which is nothing but cell constant. And this is very important formula for the numericals. Conductivity into resistance is called cell constant. After conductivity, we have done one term which is known as molar conductivity. Molar conductivity is the conductivity of the 1 mole of the solution. We have what is the difference between conductivity and molar conductivity? In molar conductivity, which is 1 mole. So conductivity of 1 molar solution is called molar conductivity. So its formula becomes kappa by C. Kappa is the total conductivity. If we divide it with the concentration, you will get the conductivity for 1 molar. But here we are multiplying it by 1 factor 1000. Why so? Because kappa is in centimeter inverse and concentration is mole per liter. So if you convert liter to centimeter, this 1000 factor comes. So it is a conversion factor. So it is kappa by C into 1000. Concentration is moles per liter. So when we convert into centimeter, so this 1000 factor comes. So its formula becomes kappa into 1000 by C. C is molarity. And this is its unit for lambda m becomes Simon centimeter square per mole. So lambda m is the conductivity for 1 molar solution. It is kappa by C into 1000. Its unit is Simon centimeter square per mole. So these are the few terms we have discussed in the last class. Then we did how conductivity and molar conductivity varies with dilution. Dilution means when you add water to the solution, how conductivity and molar conductivity varies. So the first thing which we have discussed, variation of conductivity with dilution. Conductivity always decreases with dilution. When you add water to the solution, conductivity decreases. The reason was conductivity is the conductance of 1 centimeter cube of the solution. Let us suppose you have 500 ml of water. This is 1 ml. So whatever ions are present in 1 ml of solution, that is the conductivity. It is the conductance of 1 centimeter cube of solution. Conductance of 1 centimeter cube of solution. So let us suppose 4 ions are present in 1 centimeter cube. So that is the conductivity. Now when we dilute the solution, I have added 200 ml of water in this. Now these ions get distributed in more volume. Number of ions per unit volume decreases. You have 4 ions, but when you add water, these ions get spread out in more volume. So number of ions in this specific area, it will decrease. So if number of ions are less, then conductivity also decreases. So because number of ions per unit volume decreases on dilution, conductivity also decreases on dilution. Now the question comes how molar conductivity varies with dilution. So for this thing we have done lambda m is equal to kappa into V. What is kappa here? Kappa is conductivity, V is volume. Mainly we have done kappa by C. Concentration. Concentration is number of moles by volume. If we take moles as 1, so it becomes kappa into V. So lambda m can also be written as kappa into V. So when you dilute the solution, conductivity decreases and volume increases. One factor is decreasing, another is increasing. But it is found that increase in volume is much more as compared to decrease in conductivity. So overall value increases. So lambda m increases on dilution because increase in volume is much more as compared to decrease in conductivity. So this is the reason lambda m increases on dilution. So conductivity decreases, molar conductivity increases on dilution because conductivity depends on number of ions per unit volume, that is decreasing on dilution. Lambda m depends on conductivity and volume because volume increases much more as compared to decrease in conductivity. So lambda m increases on dilution.
Lambda m is molar conductivity.
Lambda m molar conductivity. Yeah. Kappa is conductivity. The next thing we have done, how lambda m varies for strong and weak electrolytes. Advika, what is strong electrolyte?
Which ionize completely.
Electrolyte is a substance which ionizes or dissociates completely in the solution, like all strong acids, which completely dissociates in the solution, all strong bases. So, how molar conductivity varies for strong electrolyte? All of you listen carefully this point. For strong electrolyte, there is one relation, lambda m is equal to lambda m naught minus a root c. This is one equation which is known as Debye-Huckel-Onsager equation. Debye-Huckel-Onsager equation. This gives you the relation between the lambda m and the concentration, how molar conductivity varies with concentration. So when we plot a graph between lambda m and root c, graph, it's better to study right to left. When you decrease the concentration, decreasing concentration means adding water, dilution. On dilution, molar conductivity increases like this. When we add water to the solution, concentration is decreasing and molar conductivity is increasing. This is the graph for the lambda m and root c for strong electrolytes. Now, if you compare this equation with y is equal to mx plus c, here c is lambda m naught. So from here intercept, you will get the value of lambda m naught, which is, I will tell you what is that. It is limiting molar conductivity. And slope gives you the value of constant A. Now what is lambda m naught? Lambda m naught is limiting molar conductivity. And it is also called molar conductivity at infinite dilution. Conductivity at infinite, don't say it's standard molar conductivity. Not mainly you write for standard, but here it is not standard, it is limiting. So what do you mean by molar conductivity at infinite dilution? You know, when you add water to a solution, molar conductivity keeps on increasing. So when you add excess of water, a stage will come when you will get a maximum value of lambda m. After that, if you further add water, there will be no change. So that maximum value of lambda m naught is called limiting molar conductivity. Okay, if you further add any water, there will be no change in the molar conductivity. So why is it called infinite dilution? Because on adding excess of water, the maximum value of molar conductivity is called limiting molar conductivity. Smiksha, is it clear what is limiting molar conductivity?
Can you repeat it once more?
See, what is limiting molar conductivity? When you are diluting the solution, the value of molar conductivity keeps on increasing. So when you add excess of water, then a stage will come. After that, if you further add water, there will be no change. That shows the maximum value of molar conductivity. So if you further add more water, molar conductivity will not change. So that maximum value of molar conductivity is called limiting molar conductivity. Infinite dilution का मतलब है कि when we are adding excess of water, so there will be no change in the conductivity after that. Is it clear?
Yes, ma'am.
Now, what does this constant A? The value of constant A depends on type of electrolyte. Type of electrolyte means like NaCl, KCl. NaCl has charge +1, Cl minus has charge -1.
Can you scroll up for 1 second?
So Na has charge +1, Cl has charge -1. So both have 1 charge. So NaCl we can say it is 1 electrolyte. KCl +1 -1, 1 electrolyte. So they have same value of A. Similarly, MgCl2, CaF2. Charge on cation is 2 and ion is 1. 2, 1. So if the charges on cation and anion are same, the value of A is also same. So is a constant. Its value depends on the charges of cations and anions in an electrolyte. If the charges on cation and anion are same, the value of A is also same. That is for the strong electrolytes, how it varies. Now the question comes,
Ma'am, once again, what do you write? Limiting molar conductivity? One.
or molar conductivity at infinite dilution. Pavan, you tell me. Strong electrolytes are those which are already completely dissociated in the solution. Then why on adding water, Pavan, can you hear me?
Ma'am, yeah, I can.
You understood the question or shall I repeat?
Okay, ma'am, can you repeat? You cut off at on adding water or something.
The question is, strong electrolytes are those which are completely ionized in the solution. Then why on dilution the molar conductivity increases for strong electrolytes?
Because of the attraction between the ions decreases.
Yes. Then what happens due to decrease in the attraction?
The mobility increases.
Yes. So what is the next question in strong electrolytes? Strong electrolytes are those which are completely dissociated in the solution. For example, K plus Cl minus, K plus Cl minus, like this. They are already exist in the form of K plus and Cl minus. On adding water, no more ions can be formed. Then why on dilution molar conductivity increases for strong electrolytes? What is the reason for that? When you add water, these ions gets distributed in more volume. So the distance between the ions will increase. If distance becomes more, it means force of attraction decreases. Force of attraction between the ions decreases. So if force of attraction decreases, mobility increases. Mobility means movement of the ions. More the movement of the ions, more is the molar conductivity. Molar conductivity depends on two factors, number of ions and its mobility. So on dilution, the force of attraction between the ions decreases and hence mobility increases.
Ma'am, can you repeat? I need to write it down.
See, when you dilute the solution, on dilution, the force, you can see the distance between the ions will increase because these ions get distributed in more volume. So on dilution, the force of attraction between the ions decreases. So if force of attraction is less, they can move faster. Mobility increases and hence molar conductivity also increases. So that is the reason why it increases in case of strong electrolytes.
Force of attraction decreases, so mobility increases.
And hence lambda m also increases.
Mobility increases, so
Lambda m, molar conductivity.
molar conductivity also increases.
Increases. Now second thing is weak electrolytes. Others, you tell me how it molar conductivity varies in case of weak electrolytes.
Ma'am, your voice broke. Could you repeat the question?
Why molar conductivity increases, how molar conductivity varies in case of weak electrolytes? It should increase or decrease on dilution?
It will. So will increase on dilution.
Why?
Wait, wait.
What are weak electrolytes? First tell me that thing.
Sure.
What are weak electrolytes?
Like it's those electrolytes which don't like dissociate completely, right?
Weak electrolytes are those which does not dissociate completely in the solution. So what happens when you dilute the solution?
Distance between ions
No, वो
will
strong के case में है.
decrease.
This is in case of
Okay,
strong.
then
Let us suppose initially you have acetic acid. Initially only 10% of the acetic acid is dissociated. So when you add water to that, which thing will increase? Degree of dissociation will increase.
Oh.
Degree of dissociation means more amount of acetic acid starts dissociating. Initially only 10% was dissociating, but when we dilute the solution, 40% of the solution starts dissociating. So if degree of dissociation becomes more, then more number of ions will be formed and more will be the value of lambda m.
Okay.
So in this case, lambda m increases on dilution because on dilution,
The degree of dissociation becomes more.
degree of dissociation increases. So what happens due to that? More number of ions will be formed.
Yeah.
More number of ions will be formed and more will be the value of molar conductivity.
Okay.
So in both the cases, strong or weak, molar conductivity increases on dilution. Strong के case में it is due to mobility. In weak, it is due to more number of ions. Now, what should be the graph for the weak electrolytes? The graph for the weak electrolytes will be like this one. Strong electrolyte is a straight line, weak electrolytes is a curved line. The reason is because in case of weak electrolytes, more number of ions will be formed. So molar conductivity increases to a larger extent. But in weak electrolytes, but in strong electrolytes, it is just because of mobility. So it increases to a lesser extent. So that's why strong electrolyte, you got a straight line, but in weak, it increases sharply on dilution. And we have discussed one question also in the last class. Lambda m, Nityam, you have to answer this. Lambda m of A increases 25 times on dilution.
I wasn't there in the last class.
We have discussed everything. Based on that only I'm asking. Lambda m of A increases 25 times on dilution and lambda m of B increases 1.5 times on dilution. Out of A and B, which one is strong electrolyte and which one is weak?
Which one is a stronger electrolyte?
Which one? A or
Ma'am,
B?
B, right? B.
B?
Because, yeah,
Why?
even after the dilution, it has a much smaller value.
Yeah, because it increases to a lesser extent. So in case of strong electrolytes on dilution, lambda m varies slowly, but in case of weak electrolytes, it increases sharply. So that's why 25 times is for A and 1.5 times is for the B. B is strong, A is weak. So this is all we have discussed in the last class. I had repeated all the topic because next topic is related to that. Now next topic is, you can say that in strong electrolytes, we can get the value of lambda m naught from the graph. The line where it cuts the y-axis, that is the limiting molar conductivity for strong electrolytes. Nikita, you tell me, can we calculate lambda m naught for weak electrolytes from the graph?
Can you repeat what?
Strong electrolytes, we get the value of lambda m naught from the graph. That is the intercept.
Huh.
Can we calculate the lambda m naught of weak electrolytes also from the graph? If you see the graph for weak electrolyte, can we calculate lambda m naught from this also?
Yeah.
Will it cut the y-axis?
No, sorry, no.
It will not cut the y-axis because it becomes parallel to that axis. So we cannot calculate the lambda m naught of weak electrolyte from the graph because the line becomes parallel to y-axis. All of you write down this point. From here we will start the next topic. Lambda m naught for weak electrolytes not be calculated from graph because the graph becomes parallel to y-axis, or the line will not cut the y-axis. So how we can calculate lambda m naught for weak electrolyte? Yes.
Is this new note or is it
Ah,
already
from
earlier?
here, no, from here we will start the new note.
Okay.
Now how we will calculate the lambda m naught? This is called Kohlrausch law.
The graph between?
Ma'am, the graph between what?
Between graph becomes parallel to y-axis. We will write the complete word. It's parallel. Graph becomes parallel to y-axis. So to calculate lambda m naught for weak electrolytes, there is another law which is known as Kohlrausch law. Please Kohlrausch. All of you first listen carefully, then I will dictate it. Kohlrausch law states that at infinite dilution, the molar conductivity of any electrolyte, it may be strong or weak, it is always for the infinite dilution and it is always for the molar conductivity, not for the conductivity, not for equivalent, just for molar. At infinite dilution, molar conductivity of any electrolyte is equal to the sum of the molar conductivities of its cations, sum of the molar conductivities of its cations and anions. It means that each ion makes a definite contribution towards the molar conductivity. It does not depend on the nature of the other ion with which it is associated. Like lambda m naught of A. This A plus will contribute towards molar conductivity. It has a fixed value. It does not depend whether it is associated with B or it is associated with C. I will give another example. Lambda m naught of KCl. It becomes equal to lambda m naught of K plus cation plus lambda m naught of Cl minus. The limiting molar conductivity of any electrolyte is equal to sum of the limiting molar conductivities of its cations and anions. So make sure you tell me what should be the lambda m naught for CaCl2. Diksha? Yes.
So Ca2 plus and Cl minus.
Ca2 plus and lambda m naught of Cl minus. But here how many ions are there? Chloride ions 2. So it should be 2 into lambda m naught of Cl minus. So whatever number of ions are there, that you have to multiply. So this is the Kohlrausch law. Write down its definition. At infinite dilution, is always at infinite dilution, limiting molar conductivity, of any electrolyte equal to the sum of limiting molar conductivities of its cations and anions. Molar conductivities. Its definition is very important. Of its cations and anions.
What do you write after limiting molar?
Activities.
And here, limiting molar?
Conductivity.
Conductivity.
Limiting molar conductivities of its cations and anions. All of you write these 3 examples. So whenever this definition comes, you have to write the definition and one example. I'll give you another example. Yagya, you tell me lambda m naught of aluminium sulfate. What should be the value?
Lambda m naught of Al3 plus lambda m naught of lambda m naught of SO4 minus and multiply with 2.
Aluminium is 2, sulfate is 3. Because there are 2 aluminium ions and 3 sulfate ions. All of you write all the examples. Then I will tell you its application. Okay, why we are studying this. And one numerical from Kohlrausch law always comes in exam. One from Nernst equation. In electrochemistry, there are few fixed equations. One numerical from Nernst equation, equilibrium constant, or delta G. Second numerical related to this one, Kohlrausch law, or they will ask you the theory question from this part, that how strong and weak electrolytes varies with dilution, what is the reason, or from the graph they can ask something. And third numerical from the electrolytic cell. Now, what are the applications of Kohlrausch law? The first application is why we are studying Kohlrausch law, because we cannot find the lambda m naught of weak electrolytes from the graph. So we are studying it to calculate the lambda m naught for weak electrolyte. Calculation of lambda m naught of weak electrolyte. How you can calculate that? For example, lambda m naught of HCl is given to you, which is 429.5. I will give the exact values 1 minute. These values, because these are the strong electrolytes, this they have calculated from the graph and they have given you these values. Lambda m naught for HCl is 425.4 Simon centimeter square per mole. It is given that lambda m naught of NaCl is 126.4, and it is given that lambda m naught of sodium acetate, which is also a strong electrolyte, is 91. Now the question says, what is the lambda m naught of acetic acid? How will you calculate the lambda m naught for weak acid? Because this we cannot calculate from graph. This is the question. This data is given to you and you have to find the lambda m naught of acetic acid. Now first listen carefully, then you can write how to do this. It's very simple thing. Lambda m naught of HCl. Advika, you tell me how we can write lambda m naught of HCl.
lambda m naught of H plus
Hmm.
lambda m naught of Cl minus.
Yes. And its value is given as 425.4. Now, second is lambda m naught of NaCl. Pavan, you tell me how you can write for NaCl?
It'll be lambda m naught inside Na plus and then plus lambda m naught and Cl minus.
126.4. Now, third. Adarsh, you tell me how we can write lambda m naught for sodium acetate?
It'll be CH3 plus and oh sorry,
Sod-
it'll be
Na is separate. CH3
oh wait, okay, wait, I read the wrong one then my bad. It's like the screen's lagging for me, I don't know.
is it lagging for everyone? Or it's fine?
Yes, ma'am. Even I couldn't see the NA part for a while.
I was reading of CH3CO.
Yeah, same.
Okay, now tell me. CH3COO.
Minus
Hmm.
and this plus lambda naught M and Na plus.
Na plus. Now this you can write in the form of Kohlrausch law. Now you have to add or subtract these three equations so that at the end you will get just acetic acid, acetate ions and H plus ions. Remaining everything should get cancelled. Nityam, you tell me how you can add or subtract these three equations so that at the end you will get only acetate ions and H plus ions.
Ma'am, I didn't get the question. What do you mean how we can?
These are the three equations, right?
Yeah.
You have to add or subtract the equation, maybe 1 plus 2 minus 3, maybe 1 plus 3 minus 2, so
Okay.
that at the end you should get only acetic acid, acetate ions plus H plus ions. Remaining everything should get cancelled.
Then I think see Na goes with Na, Cl goes with Cl. Then
Which equation we can add and subtract?
first equation. Oh, so I'm not understanding this part, ma'am. I just understand that H comes from the first equation and CH3.
Hmm. So we will add 1 and 3, right?
Yeah. Yeah.
दोनों को add कर दो, you will get CH3 and H. So Na plus and Cl minus extra आ रहा है.
Yeah. And
So
then
we
we
have to
-2.
minus 2. Yeah. So you have to add or subtract the equations so that you can get only acetic acid at the end. So when you subtract 2, Na plus goes with this Na plus, Cl minus gets cancelled with Cl minus. So what you will get? Lambda m naught of H plus lambda m naught of acetate ion, which is nothing but when you add it, it becomes acetic acid only. Down this numeric, then I will restart my board. Acetate ion, which is equal to, so similarly you have add or subtract the values also. So 425 plus 91 minus 126.4. So you will get 390.5. That is the answer for the Simon centimeter square per mole. So this is the value for when you add these acetic acid, CH3COOH, which is 390.5. Simon centimeter square per mole. So this is the Kohlrausch law numerical. They will give you the data for 3 strong electrolytes. You have to find the weak one. So you have to add or subtract the equations so that at the end you will get your aim equation. I will give you one more example right on this one. If required, you can multiply with some number also, 2, 3.
The application of this law is coming for the exam, right?
Yes. This law completely, that is the last topic. So this comes in exam completely, this topic. There are 2 more applications.
Ma'am, can you just explain how like You got 390.5 again.
What we have done, we have added first and third equation, right?
Yeah.
So 425.4 plus 91. That is a
and
value.
then minus 160.
Yeah, minus 126.4. Yeah. Oh, I think 0.5 will not come if I'm not. 390 is coming because in book the value was 425. 9 is given. Just check whether you are getting 390.5 or 390. Should be 6, 11, 516 minus 390 will come. Is it done? All of you are done with the writing part?
Yeah, done, ma'am.
Okay, now 1 second, I will restart my board then. Write down the next one. It is given that lambda m naught of NaI write it. Lambda m naught of NaI is given, which is 12.69. Lambda m naught of CS3CONa is given, which is 9.10. Lambda m naught of Mg CS3CO twice Mg is given, which is 18.78. You have to calculate the lambda m naught of MgI2. All of you solve this one. Same type of question, just little bit variation is there. All of you solve it and tell me the answer for the first one. Then you solve the second numerical. What should be the first step?
I'm writing the equation.
Nikita, you are here?
Yeah, ma'am. So Na plus and I minus, then CH3COO minus and Na plus, and then CH3COO whole 2 minus and Mg plus.
have to find the lambda m naught of this one. Lambda m naught of mg2 plus, you can write in this form, plus 2 into lambda m naught of I minus. This you have to find. Yagya, what should be the next step?
Now you see what to add and subtract.
Here we can directly add or subtract, or we need to multiply with some number somewhere.
Yeah, you multiply also. But should I tell the
You got it, like you have done that one, addition subtraction.
yeah
Now tell me.
yeah I didn't do the final calculation, but
Just tell me the
so-
addition subtraction part.
so the third equation minus 2 of the second equation plus 2 of the first equation.
Yes. So first two equations you have to multiply by 2. Why so? Because you need 2 lambda m naught of I minus. So we will, to get 2 I minus, we will multiply the first equation with 2. So it becomes 3 plus 2 into 1. Second equation gets multiplied by 2. Minus, because we don't want acetate ions and we don't want sodium ions. There are 2 acetate ions and 2 sodium ions in the first and third equation. So second equation also you will multiply by 2. So 3 plus 2 into first equation minus 2 into second equation. So what is the value of third equation? 18.78 plus 2 into 12.69 minus 2 into 9.10. You will get the answer as 25.96 Siemens centimeter square per mole. So first you write the equations, then you see what is your aim thing. So this is the aim equation. You want Mg2 plus and 2I minus. To get 2I minus, we have multiplied the first equation by 2. And then you add first and third equation. After addition of this, you have 2 acetate ions and 2 sodium ions extra. So we'll subtract the second equation after multiplying it by 2. .96 is the lambda m naught of MgI2. Now those who are done with this one, do the second one. It's simple, 1 second. The lambda m naught of aluminium sulfate is given. You have to find the value of aluminium 3 plus. Sulfate ion value is given. Just tell me the direct answer, all of you.
You've written 858, right?
858, yeah. Aluminium sulfate is 858. Sulfate is 160.
Uh, 189.
Yeah, ma'am, 189.
Yes, answer is 189. Advika, what is your answer? You solved it or?
Ma'am, same.
Samiksha, you got the answer?
Yes, ma'am. It's the same.
Nikita? Into aluminium, you have to find 3 into 160. That is simple thing. So 858 minus 480 by 2. So I think 189. Simon, write the units if you have not written. Units are very important. That is a lambda m naught of Al3 plus. So like this, you have to solve the questions of Kohlrausch law first application. Now, second application. Second application of Kohlrausch law is calculation of degree of dissociation. First application was we can calculate the lambda m naught for weak electrolytes. Second is we can find the degree of dissociation. Degree of dissociation means fraction of molecules that undergoes dissociation in the solution. Weak electrolytes are not completely dissociated. So how much fraction of molecules are dissociating in the solution? That is degree of dissociation. It is denoted by alpha. So alpha is equal to lambda m by lambda m naught. What is lambda m? Normal molar conductivity. They will give you direct value. If direct value is not given, you can find using the same formula kappa by C into 1000. If they give you molar conductivity, you can substitute. But if they give you conductivity, then you find molar conductivity and then substitute it here. And lambda m naught is limiting molar conductivity. They will give you direct value. If direct value is not given, you can do the lambda m naught of cations plus anions. They will give you the value of cation and anion separately. You will add it and substitute. So degree of dissociation is lambda m by lambda m naught. It should always be less than 1 because it is a fraction. Now, third and the last application is calculation of dissociation constant. Dissociation constant. This is same formula as you have done in solutions. Dissociation constant is equal to C alpha square by 1 minus alpha. What is C here? C is concentration, which is molarity. Alpha is degree of dissociation. And here you don't have to ignore alpha in the denominator because solution mein mainly we were ignoring that. Because in these numericals, alpha value is not very small. Like you will get either 0.5, 0.6, 0.2. So these are big values. So we cannot ignore in the denominator alpha. If it is very small value like 0.00001, then you can ignore it. But mainly in all the numericals of Kohlrausch law, you will get alpha as a big number. So this is all about the Kohlrausch law. Now I will give you the numerical based on these two formulas. Now write down the first one. Conductivity of, those who were not there in the last class, topic we have revised, but there were many numericals based on that formulas. So you just watch the recording and solve that numericals. Conductivity of 0.00241 molar acetic acid is 7.896 into 10 raised to power minus 5 Simon centimeter inverse. Calculate molar conductivity. I'm writing in short. And if lambda m naught for acetic acid is 90.5 Simon centimeter square per mole, calculate dissociation constant. What is it? Dissociation constant. All of you solve this one. And don't use the calculator. Do the calculations manually.
Could you show the formula again?
Yeah. Sorry.
Ma'am, can you just excuse me for 1 minute? I'll be right back.
Solve these two numericals. For Nernst equation and this formula, they give you very simple numerical where you have to just substitute the values in the formula. The only thing is you should know the formulas properly. Advika, what is the first answer for lambda m?
I got 32.
Exact 32 or point something?
I don't know, I got 32.
Okay. Nityam, what is your answer for this one?
I didn't get it.
Numerical you didn't get it or answer you didn't get it?
Answer didn't get it. Wait, I'm trying to do it. Just
It should be 32.76. It is kappa by C into 1000. Kappa is 7.896 into 10 raised to minus 5 by 0.00241 into 1000. So when you solve it, you will get 32.76 Simon centimeter square per mole. Nikita, you're done with the second calculation?
No, I'm still doing the first one. One second.
In first calculation, I will show you in case you are confused in the question how you can do that. It was 7.896 into 10 raised to power minus 5 by 0.00241 into 1000. That was the thing. First, you solve the decimals. So if I remove this decimal from here, it becomes 10 raised to power minus 5. And if I remove this decimal from here, it becomes divided by 1000. So first you do like this. So 1000 gets cancelled, minus 5 minus. So it is 7896 by 241.
What's unit for dissociation constant?
No units for
Oh, yeah, it's
degree of
not constant.
dissociation as well as dissociation constant.
Oh, yeah, my bad.
So you can directly divide. Don't cut it on some number. That is divisible on 3, 5, 7. Divide it directly. So 7. So it will come around 3, 3, 12, 7.
Your screen is black. Okay, never mind. It came back. Yeah, I got it.
So it's like this. When you divide it by 2, 84, 0. Then it is 18. So it should go around 8, 8, 32, 12. But 7. Like this, you can do the calculation. It will come 8. So it will come 32.76. So here also in the next step, divide 3276 by 390.5. So just remove the decimals and then divide it directly. You get any one of you get the alpha answer? Tell me.
0.083.
Yes, 0.083. Next number will be 9. So either you can stop it at 83 also, 839 also, because it becomes round off to 84. Now last K. Concentration is 0.0241 into this is a big calculation, 0.0839 ka square by 1 minus 0.0839. So this you have to solve to get the value of K. Now here you can round it off. You can make it as 0.084. And then you can solve it. Okay, here you will get approximately 1.85 into 10 raised to power minus 5. It was the substitution thing, but calculation takes time. Remaining two calculations were simple, but dissociation constant calculation is always big because you have to do alpha square multiplication and then division. Now do the last question, then I will start the next topic. The molar conductivity of this solution is this one. Calculate degree of dissociation and dissociation constant.
to 349.6, right?
But where? It is lambda
Yes.
h plus is 349.6. Nityam, tell me the first step for the second numerical. We have to calculate first. Let me say. It's not here. Nityam? Okay, who will tell me? Pawan, you tell me what should be the first step?
Okay. So first will be lambda m naught of HCOOH is lambda m naught of HCOO minus plus lambda m naught of H plus.
What is that value comes? You have added both the numbers?
No. I 1 second. It's 295.
Huh?
Isn't it?
After addition, you will get.
Oh, I subtracted. 1 second.
I think this one.
Yeah, that one.
So, Miksha, what is the next step?
Now we have to find the dissociation constant. So then we use the formula C minus alpha square divided by 1 minus alpha.
C alpha square by 1 minus alpha. For that, first we need to calculate
Yeah,
alpha.
that's right. So then alpha is equal to lambda m divided by lambda m naught, which is equal to 40.1 divided by 404.2.
Yeah. You have done that calculation or not yet?
0.114.
Correct. That is alpha. Nikita, what is the, tell me the values for the dissociation constant.
So 0.025 into 0.114 whole square by 1 minus 0.1.
Advika, what is the answer of K? You got that or you're still calculating?
Ma'am, still doing.
All of you do it and tell me what is the final answer for this numerical. Then I will give you an idea about the next topic, but that topic we will do in the next class. So you will get the answer as 3.67 into 10 raised to the power minus 4. So these calculations, you just practice it. Now next topic in this chapter, we are done with 2 topics. Now the third topic of this chapter is electrolytic cell. This is the next topic. Now, what was the electrochemical cell? The cell which converts chemical energy into electrical energy. Now, what is electrolytic cell? It is the reverse of that. It is a cell which converts electrical to chemical.
But this part is not coming for the exam, right?
No. For exam, it is coming till here. That Kohlrausch law was the last thing. Which converts electrical to chemical energy. See, in electrical to chemical means the reaction, there are some reaction which cannot take place on its own. You need to give some energy to the reaction so that this reaction can take place. So this, when we give the electrical energy, then only the chemical reaction is taking place. So that is electrolytic cell, which converts the energy comes from electricity into chemical energy. Who will tell me whether is it for spontaneous? Others, you tell me. Electrolytic cell should be for spontaneous reaction or for the non-spontaneous reaction? We are giving electrical energy for the reaction to take place. So is it for spontaneous reaction or non-spontaneous?
Wait, so I didn't get the question.
See, electrochemical cell we have done. It is for the spontaneous reaction because it converts the chemical energy to electrical energy.
Yeah.
This cell is converting electrical to chemical, means we need to give some energy for the reaction to take place.
Yeah.
Is it for spontaneous or non-spontaneous reactions? Electrolytic cell.
Non-spontaneous.
It is for non-spontaneous, the reaction which cannot take place on its own. We need to give electrical energy for the reaction to take place. So it is always for non-spontaneous. So this is the second difference between electrolytic and electrochemical cell. If you remember, we have done delta G value is negative for electrochemical cell because the reactions were spontaneous. In this case, the Gibbs free energy change value is positive because reaction is non-spontaneous. So the Gibbs free energy change for electrolytic cell is positive. And the last point, in electrochemical cell, you have done anode is negative, cathode is positive. Here it is, anode is positive, cathode is negative. Electrolytic cell ka example maybe you have done in lower grades, that the electrolytic refining of copper, it takes place in one beaker, one electrode is impure copper, another was pure copper. You have done that
Negative for both.
Anode is negative, cathode is also negative.
by mistake. Anode is positive, cathode is negative. That line was missing. All right. So these are the 4 points of difference between electrochemical and electrolytic cell. Electrochemical cell takes place in two separate beakers joined by a salt bridge, but electrolytic cell takes place in a single beaker. I will give you one example of electrolytic cell which we have studied in lower grades. Okay,
So
here,
this one.
no salt bridge because it is taking place in a single beaker. This is copper sulfate solution. If you remember this, there is one electrode which is dipped in that, and there is a battery. Positive terminal is anode, negative terminal is cathode, and anode is impure copper. This is an example I will give you. Impure copper, which you have to purify, and cathode is pure copper. So what happened when you pass the electric current? The at anode there is always an oxidation. At anode, copper gets oxidized, converts into copper ions, and goes into the solution. Copper gets oxidized to copper ions and goes into the solution. And what happens at cathode? These copper ions gets reduced and gets deposited at the cathode. So at anode, copper is converting into copper ions, and at cathode, copper ions are converting into copper and depositing there. So you can see that ultimately whatever the pure copper is present on this side, it gets deposited at cathode. Only impurities are left behind at anode side. That is known as anode mud. So this, this is an example of electrolytic cell. Okay, when we pass the current, reaction takes place, anode gets oxidized, cathode gets reduced. And this we can also use for the electrolytic refining of copper. Refining means to remove the impurities from the copper. So what we have to study in electrolytic cell? In this electrolytic cell, we will study about the quantitative aspects. Quantitative aspects means quantity. How much we have just checked that copper is going into the solution. Here copper is deposited. Now how much copper is deposited at the electrode, that we have to check using this quantitative aspects. Okay, what is the amount of substance deposited or liberated at any electrode, that we have to study under this topic. What are the quantitative aspects of electrolytic cell? There are two laws for that. We will just do one law today, Faraday's first law. Okay, leave it. I will not start this topic because you have another class after this. Next class maybe we will do. I will just revise once. Faraday's first law states that whatever amount of substance deposited at any electrode, it depends on how much current we are passing through the solution. More the amount of charge passed through the solution, more amount of substance gets deposited. So amount of substance deposited is directly proportional to current passed through the solution charge. Okay, I will explain this topic in the next class. Leave it. We will just revise once what we have studied today. Okay, so today we have started from the conductivity. We'll just quickly revise. Advika, you tell me how conductivity varies with dilution and why.
Ma'am, conductivity, like with